Okay, so let's begin. So this is a definition of the eigenfunction of the Koopman operator associated with eigenvalue lambda. So this basically means that this Koopman operator leaves this function phi lambda invariant. So using the definition of this Koopman operator, one can rewrite this as simply saying that this is true, right? So phi lambda t of x is same as lambda times phi lambda of x, right? That's so now let's see. Let's try to do some examples, and in this through this example, I will tell you what are some of the challenges associated with computing this. Okay, let's start with a simple example. So let's say I have an example which is simply a one-dimensional example, which is rotation on a torus or rotation on a circle. Xt plus 1 equals xt plus omega, and then this sort of mod 1. Okay, what does it mean is that you have a circle and you are actually moving on the circle. At every time you take a step of omega, and once you cross 1, you come back to 0. Okay, so that's what this system is. It's very easy. So think about this 0, 1, right? So you let's say you have x0, your next point will be, you jump to x1, which is x0 plus omega, and then you keep on doing it. If you exit, then you come back, you do a mod, that means this point is identified with this point. You come back again to 0, 1. So you bring it back to 0, 1. Right? Now, this looks very simple, but actually is very complicated. In fact, my PhD thesis actually was based on this simple math. So if you actually perturb this, I mean, you get all sorts of crazy things. And in fact, if you think a little bit about it, like since this is mod 1, what happens is omega is rational. What kind of behaviors you expect to see? If omega is a rational number, what do you expect? If you start any point, if omega is rational, you'll come back to the same point after some time, because omega is rational, right? So you multiply enough n times that omega will give you back the same, so you come back to the same point. Now what happens if omega is irrational? Now if omega is irrational, this orbit of this is actually dense. You'll never come back to the same point. So starting from any initial condition, you pretty much, if you stay long enough, it'll sort of cover the whole circle. It'll get to each and every point of the circle, get arbitrarily close to each and every point of the circle. So the orbit for omega irrational will be dense in the 0, 1. Right? Dense, as I described, like if you take any point in 0, 1 and construct any epsilon ball, pick any arbitrary small epsilon, pick any arbitrary small point, the orbit for this system will come within the epsilon neighborhood of that point. Okay. Anyway, so that's not the main focus, but so this dynamics, it's actually evolving on a circle, which is a manifold, which then that's why, although this is like if I forget about the mod 1, this is like affine linear, right? Because xt plus 1 is xt plus omega. Omega is a constant term. So it's kind of affine linear, but because it is mod 1, it is actually nonlinear. Because it is evolving, so you can have a linear dynamics on a nonlinear manifold, it is still nonlinear. Okay. So now, if I want to describe this using Koopman, so what I do is actually, let's say if I pick these functions like a Fourier function, Fourier basis functions. So what I do is I take these functions which are fn of x is e to the I n x, where n belongs to the integer. Okay. Now see what is the action of this is on this function with the Koopman operator associated with this, right? So kappa. So let's call this as your s of xt. Kappa fn of x is fn s of x, which is e to the I n x plus omega, right, which is e to the I n x e to the I n omega, which is same as e to the I n omega fn of x. Oops. E to the I n omega fn of x. So kappa fn of x is e to the I n omega fn of x. So what does this tells you? This Fourier functions, Fourier bases, or like this, are basically the eigenfunctions with eigenvalue e to the I n omega, right? These are the eigenfunctions with eigenvalue e to the I n omega. That's because it fits this definition of the eigenvalue eigenfunction. Another thing to notice is that if omega is rational, then you have only finitely many eigenvalues. If omega is irrational, then you have continuous infinitely many eigenvalues. Okay? Now, I'm sorry, I should not say finite eigenvalues. You'll still have infinite eigenvalues, but these are, so if omega is rational, there are still infinite eigenvalues, but these are countable ones. These are actually discrete eigenvalues. Okay? But if omega is irrational, this becomes a continuous eigenvalue. This is what I was talking about, the spectrum being either discrete or continuous. Okay? So this is a very simple example. Another example that you can consider, you can ask, okay, what does Koopman does for a simple linear system? So let's say I have a linear system. I mean, how will the Koopman look like for a linear system? So let's say I have a two-dimensional linear system. Let's assume it's a diagonal A matrix, right? Now it has two eigenvalues, lambda 1, lambda 2. What does the Koopman operator for linear system will look like? Right? And then what will be the eigenvalues of that Koopman operator will be? Right? Although the linear system has only, if it is a two-dimensional system, let's say example 2 of a linear system. So let's say I have a linear system which is xt plus 1 equals some lambda 1 xt, and then yt plus 1 equals lambda 2 yt, right? So this is like lambda 1 0 0 lambda 2 xt yt, and this is kind of, this example will kind of tell you what is really happening with these eigenvalues of the original system. Okay, so this is your linear system. Now, I want to actually consider a Koopman operator. So, I mean, I skip one step, is that Koopman operator is an abstract operator, right? So, until and unless I tell you, I mean, the way you realize this operator is by putting some basis on the underlying function space, right? And now, if you change the basis, the realization will change, although the underlying operator is the same, right? It's like depending upon what glasses you wear. So if you wear green glasses, then everything looks green. If you wear red glasses, everything looks red. So glasses are like your basis functions, and the world outside it is the reality, but or like the operator. But depending upon the basis or depending upon the glasses you pick, the realization changes, right? So same thing now with this. So I have to pick some basis. So let's pick, since it's a linear system, I will pick a polynomial basis. Okay. So let's say I pick a basis which is, so this is a space of observables. So observable functions. I pick f m n x y as x power m, y power n. M and n are natural numbers. Okay, so these are my basis functions. Okay. Now with this basis, how is this Koopman operator will look like? In fact, the way I am constructing the basis, it turns out that in this basis, I mean these bases are basically the eigenfunctions, just like in the previous case. This space of observables happens to be just the eigenfunctions. Okay, and you can see the following. So let's call this as your A zt, where z is the vector x and y. So now kappa fmn of xy will be fmn of what? Lambda 1 x, right, and lambda 2 y, right, which is lambda 1 x power m, lambda 2 y power n, right? If you want me to slow down, I can. I think this is sort of fairly straightforward calculation, right? So this becomes lambda 1 power m, lambda 2 power n, x power n, x power m, y power n, right? So what does this tells you? This is lambda 1 power m, lambda 2 power n, f m n x y. So what does this tells you? Right. So what does it tell you about the fmn? This polynomial basis functions. These are the eigenfunctions. What is the eigenvalue? Lambda 1 power m, lambda 2 power n. You see what is happening? How do you get these infinitely eigenvalues now? So your linear system has only 2 eigenvalues. But how are you getting this other eigenvalues from the Koopman operator? By just raising them to some natural numbers. So if you take m to be equal to 1, n to be 0, then you get the original eigenvalue. Similarly, if you take m to be 0 and n to be 1, you get back the lambda 1 and lambda 2 as an eigenvalue, but not only those are the eigenvalues of the Koopman operator. So the eigenvalues of the linear system are also the eigenvalues of the Koopman operator, but then the eigenvalues of the Koopman operator has this algebra property. That means if you take lambda 1, lambda 2 as an eigenvalue of a linear system, then lambda 1 power m, lambda 2 power n are also eigenvalues of the Koopman operator. So this is basically what is called as the Thomson algebra. Okay. So this is how you are getting all the other eigenvalues, you see. So how you get all the other eigenvalues, or infinitely many of them, yeah, and in fact, I mean, because we just happen to pick a very good basis that you see this thing very nicely, right? If I choose on, let's say, some other basis, like a trigonometric basis, then I may not have able to see this thing so clearly. This example, it was very trivial, but so anyway, I think the point is that the basis plays an important role, and secondly is that for simple linear system, you get the eigenvalues of the Koopman operator are the same as the eigenvalues of linearization, so not linearization of the linear system, but also the higher powers of the eigenvalues are also the eigenvalues of the Koopman operator. Good? No, they will not. They are the inherent properties of that. It's just that in some bases it may be easier to see, but in some you may not be that lucky, right? And that's, I mean, choosing the right basis is more than half the battle, right? Okay. So these examples were very simple examples, which is, so results are not very surprising. Let me do one more example, and I think this example is example 3. So this example is again a two-dimensional system example. xt plus 1 equals xt, and then yt plus 1 equals yt plus xt square. Okay, you may put some constants, but I mean, it doesn't really matter. Okay, so now I choose a basis for this. You see what will happen. I choose the following basis. Okay, so I choose the basis functions as psi of x as I put a constant 1, x, y, and x square. So these are my basis functions. Okay, I just pick them. Okay, you could pick something else. The reason I picked this will become clear later. Will become clear soon. But I picked this basis function. Now, what I want to do is actually I want to find a representation of the Koopman operator in this basis. Okay. Now, so what I want to know is that what is psi plus of x is. Okay. Okay. Psi plus of x. What does that mean is that if with this basis, so I told you how the scalar observables, the scalar functions evolve under the Koopman. Now I'm taking a vector function. I mean, vector function will again behave the same. So instead of taking one function at a one time, I'm taking n functions. In this case, 1, 2, 3, 4, 4 functions at the same time. So that's why I'm writing a psi plus. We can also do it individually, right? So okay, you will see that. So if there are questions, I will answer it, but if not, then I just skip it. So what will be the 1 plus will evolve to? 1 plus will evolve to 1, right? Because so 1 plus will evolve to 1, right? What is x plus will look like? I mean, the plus I'm saying is for the t plus 1, okay? So I don't know what's the, okay, so let me use, because this may confuse. So these are basically a function, but these are actually here when I write down system. These, you think of these as, you don't think of x and y as a function, you think of them as a coordinates, right? So when coordinates are also actually coordinate functions. Okay, so there are, if you do differential geometry, then you know that they make a distinction between coordinates and coordinates functions. So really, when you write down this x and y dynamics in state space, you think of them as a coordinate, but they are actually coordinate functions. So what it means is that x t plus or x is basically a coordinate. So you are in two-dimensional space, you pick the x coordinate of a point, right? So to make the distinction, instead of calling them 1, x, y, x2, I will call these at psi 1, psi 2, psi 3, and psi 4 as a function of, sorry, this I should call it as z. So what is my z? Z is my x and y as a vector function, right? Vector. So psi 1 is a function of z, psi 2 is a function of z, psi 3 is a function of z, and psi 4 is a function of z. And what is psi 1 of z? Psi 1 of z is 1, psi 2 of z is x, psi 3 of z is y, psi 4 of z is x squared. Okay. So now what is psi 1 Koopman operator acting on psi 1 of z will be just psi 1 of z, right? Because psi 1 is just 1, Koopman acting on 1 will just give you 1. So now Koopman operator acting on psi 2 of z will be psi 2 of, let's call this as the mapping t of z. T of z, which is, so psi 2 is x and t of z is just the first coordinate. So this will again be psi 2 of z, right? Because x t plus 1 is again xt. Make sense? I mean, there is an easier way to understand this. Let me do this and then I'll tell you what is happening. So psi 3 of this is simply, if you look at this, it is y plus x square, which is psi 3 plus psi 4. Okay? And now on psi 4 of z is x2 square, which is what? So psi 4 of t of z, which is psi 4 is x square, which is again x, right? So it will be again the psi 4 of z. Okay. So you see what is happening. So Koopman operator, so there are two things which is important to understand here. Koopman acting on these basis functions, so it has to do with two things, okay? So there is an underlying dynamical system, which is this nonlinear system, and then there is a choice of basis. For this example, the dynamical system is such that if I use this basis, I get a finite dimensional Koopman operator, or the Koopman operator becomes a matrix with this basis. For this example, if I choose a different basis, I may not have gotten a finite dimensional operator, finite dimensional Koopman matrix. Okay? It's just that the structure of the system is such that, and the choice of basis is such that I see a finite dimensional realization. Because if I write down this in terms of matrix, then basically what it's saying is that psi 1 of z goes to psi 1 of z, psi 2 of z goes to psi 2 of z, right? Psi 3 of z goes to psi 3 plus psi 4, and then psi 4 goes to psi 4. Right? So that's your matrix. Now you can write down this matrix in a different form. Okay, you can write down, and I think I will write down. I'll tell you why I'm writing it like this. Okay, so if I want to write the matrix correspondence, which I denote by k, the k will be 1 0 0 0. Okay, and this will be 0 1 0 0, and then this will be 0 0 1 1, and this will be 0 0 0 1. Okay, so this is the. Let me tell you why I'm writing it like this. Okay. So how am I writing this like this? Psi 1 stays psi 1, so that's why this first column is 1 0 0 0. Second, psi 2 stays psi 2, so that's why 0 1 0 0. Third, psi 3 becomes psi 3 plus psi 4. This is 0 0 1 1, and psi 4 stays psi 4, so 0 0 0 1. So I'm writing in terms of like a transpose, so to say. So reason is the following, I'll tell you. So the way you can actually visualize this is the following. So I want to find the matrix representation of this operator, okay? That's my goal, right? So matrix representation of operator. So what we are doing is, to find a matrix representation of operator, I first put a basis, right? Just like the way you do in linear algebra. You put a basis. So I put a basis psi as a basis on the domain and the range space, right? Now, what is the matrix representation of the Koopman operator does? It's a matrix. It cannot propagate function. So what it does? So you have this function space. This kappa is the Koopman operator, right? So it takes function to function, but what I'm now doing is I'm putting a basis and converting it to a finite dimensional space. In this case, a 4-dimensional space, right? And this, right? So I want to know how the k acts on function, but what I'm doing is I'm first putting a basis and converting to a finite dimensional space. And then I have construct a matrix K. So this is K and this is kappa, if it is a confusion. So this is kappa, which is an operator, which is like a God, and this is the realization of the God. K is a matrix, right? I put a finite dimensional matrix, finite dimensional basis, so that this infinite dimensional function now becomes a finite dimensional vector space. And now, so what does this K does? K is acting on from a finite dimensional vector space to finite dimensional vector space. So what does K does? Thinking very pedantically, approximate Koopman operator, but even more pedantically, what it does, it takes a vector and map it to a vector, right? What does the vector is? How that vector connects to the function? So if you give a vector to this K, it gives me another vector. So what is the vector is? What is a vector? Vector is, in this case, the 4-dimensional. So vector have 4 entries. So what are the entries are? So the entries are basically the coefficient in the expansion of the function. So think of this think of the entries in the vector as the coefficients which are used to expand the function. Right? So given any function, in this F space, what are you doing? So by putting this basis, what we are really doing is that given any arbitrary function f of x in this function space, I want to write this as linear combination of the basis functions. Right? What are these alpha i's? Alpha i's are the coefficient used in the expansion, and those are precisely the vector constituting in R4. Make sense? Yes. Right now I'm just constructing a finite dimensional. I'm just constructing a projection of that. I'm not trying to, so think of this as actually a finite dimensional approximation of the infinite dimension, right? And it turns out that the finite dimension is enough in this case. And that's the second point I want to draw home, right? So, of course, they don't span the entire infinite dimensional function space, but they form a basis for the finite dimensional subspace of this of the infinite dimensional vector space, right? So this coefficient which are used in the expansion of this arbitrary function using this basis, finite basis, are nothing but the vectors which are used in a propagation. So what is the matrix approximation of Koopman operator does? It is basically propagating those coefficients, right? So the way it works is, okay, I gave you some initial function f0. What you do, you project this f0 onto this finite basis, and these alpha i's are the coefficient in the expansion. Now you take these alpha i's, now k acts on these alpha i's, right, and gives you new coefficient, let's say beta i's. Now you take those beta i's and do f1 of z as beta I psi I of z. So that's your new approximate function which has been propagated by the Koopman operator. That makes sense? And how do you go from alpha I to beta I? Alpha I to beta I using k, right? So you have this alpha 1, alpha 2, alpha 4, and that goes to beta 1, beta 4, right? And that is done using this matrix k. And this multiplication is either you can multiply it from right or you can multiply it from left. The standard convention is you multiply it from the right. So this k alpha equals beta, right? Now what is a function? Now I want to get a function from this. So function is u2 psi transpose from the left and psi transpose from the right. Make sense? So that's why this matrix is written in a transpose form, because the functions are multiplying from the left. The coefficients are multiplying from the right. Okay? So that's like a small detail. You can, if you do use functions from the left, and then you can write it in terms of k transpose and so on. Okay? Does that make sense? I'm confusing because I'm trying to tell you all the small details, and sometimes you get lost in those details and miss the big picture. The big picture is that, at least for this example, is that this example is constructed in such a way that if I use this particular basis, the Koopman operator for this example turns out to be a finite dimensional matrix. That's the big picture. Okay? And it has to do with two things. It has to do with the system and it has to do with the basis. Okay? Both has to sort of work together to give you the finite dimensional Koopman. Koopman is an infinite dimensional operator, but for this example, it just turns out, it just happens to be that I was smart enough to find the right set of bases which gives me a finite dimensional matrix representation of this Koopman operator. I may not be lucky all the time, or I may not be smart all the time, because the system may be different. That makes sense? Okay. Yes. That's a good question. Nobody knows. For practical systems, this will not happen. Okay? Like, take a simple example of inverted pendulum. I mean, I should not say that, right? Take a simple example of inverted pendulum, which, and these problems are actually kind of like, all sort of things are actually, the way I see, they're all sort of connected. Take a simple example of inverted pendulum, right? We did this, right? It's a two-dimensional state space. where you have all these nice circles and so on, so forth, right? It's a nonlinear system. It was a continuous time, but forget about that fact. You can ask, okay, can I find a Koopman coordinates, or can I find a right set of basis functions in which I can write the nonlinear example as a linear example, as a finite dimensional linear system, right? That's what it is. Of course, it's infinite dimensional linear. We know that. Can you write it as a finite dimensional linear? I would say yes. I know the basis which can be used to write that as a linear system. And whatever basis, can you tell me, like, if you know the physics, if you are good at physics, you will know the basis for the invariant pendulum example without damping. You use energy. If you use energy functions, say energy functions are actually level curves. So if you write down this pendulum equation, instead of in the Cartesian coordinate, if you write down them if you use the Hamiltonian, or if you use the, it comes with some, I would say, like quotation, but I'm sort of oversimplifying things. But let's say if you use the Hamiltonian, if you use the energy to describe the equation of motions, then the equation of motion look like, let's say energy is I, then you get I dot equals 0 because energy is not changing. I dot is 0, and it's a two-dimensional system, so I need to have two states and omega. So basically, instead of writing the system instead of writing in the Cartesian coordinate, if you write in a polar coordinate, a nonlinear polar coordinate, then you get a system which is actually what is called an integrable system. So this problem of actually able to write a Koopman operator as a finite dimensional matrix is actually sort of a very deep problem which has to do with the integrability of a system. And for some systems we could, but not for all systems. Okay. So the simple example of invariant pendulum, we can actually work around and actually able to find some right coordinates where it could work. And if you believe that everything in this world is basically just coupled inverted pendulum, then we have solved the problem. But yeah, it's not that. But in general, it is not. So basically, the way you think about this diagram is kind of a commutative diagram. So you have F0. I want to know how the F0 will go to F1. The way you do that, you first project the F0 onto finite basis, get this coefficient alpha, propagate this coefficient alpha to get the beta, and then go back, construct this F1 using beta, right? So you sort of go back. So this is a commutative diagram. So instead of mapping function F0 to F1, you go take a projection from F0 to alpha, propagate this alpha to beta, and then move back from beta to F1. Yes? Exactly. So what is the right? It's basically saying that if somebody gives you a nonlinear system, and that's exactly the point I was trying to make, that you have a nonlinear system, that's because you decided to actually modulate a nonlinear system. It's not the real thing is nonlinear. It's just that you don't know the right way of modeling it. That's why you end up with a nonlinear system. If you are smart, if you know the right coordinates to represent that system, you may have written a model which is a linear model. The same thing is happening here. And you know that very well, fact, from your linear system course as well. In linear system course, when you write down the equation of motion, let's say for RLC circuit, what are the states that you use? You use capacitor charge across the capacitor and current through the inductor as the states. Why? Because that makes physical sense. If you use that as a state, what happens? You get an A matrix which is all coupled, right? Which is all coupled. But then we know the power of state space is that I don't have to stick to the capacitor voltage as a state, inductor current as a state. I could do a linear combination. And when I do linear combination, suddenly the matrix becomes decoupled because we are smart enough to find the right coordinates. The analogy I'm trying to build is that for a linear system, you get a coupled system of equation, but then you find the right coordinates, you get a decoupled system of equation. Similarly, for nonlinear system, you start with the physics coordinates based on the physics of the problem, you end up with a nonlinear system of equation. If I know right set of coordinates, just like I was telling you for the inverted pendulum, you use the position and velocity as a coordinate and you ended up with these equations which are all coupled, which are nonlinear. But if I use the energy as a coordinate, I get a decoupled equation. I dot equals 0, theta dot equals omega I, which is perfectly beautiful equations as far as I'm concerned. which are completely integrable. You can write down the solution explicitly. Inverted pendulum example, you cannot write down a solution explicitly. But if I use energy as a coordinate, I can write down a solution explicitly. Right? So yes, so in this case too, finding the right basis is more than half the battle. Right? And I think nobody knows how to find the right basis. In this example, I just cooked them up such that the right bases were evident. Okay? So now I'll give an example where things doesn't work the way you want. That means there is no finite dimensional Koopman. All you can do is actually find the best possible approximation of Koopman in that basis. Okay? Make sense? Any questions? So let's get back to the logistic map example, right? The one which we did before. Okay. Of course, now once you have this matrix, what you can do? You can find the eigenvalues, eigenvectors, right? You find the eigenvalue, eigenvector. Let's say V is the eigenvector. Then what will be the eigenfunctions? So let me just complete that. So now I have this K matrix, right? I can find KV equals lambda V, right? So this is the eigenvector. What will be the eigenfunction? Phi lambda of X or Z will be, what will be phi lambda of Z? Yes, so it will be the psi transpose V, where psi are my bases. Right? So this is how we get the eigenfunction from the eigenvectors. So you see, the original system was two-dimensional nonlinear. I ended up with the four-dimensional Koopman matrix. Okay, I ended up with a four-dimensional Koopman matrix. Now later on, I will talk about like I can actually. Okay, so maybe I'm sort of going a little ahead of myself. You can ask yourself, I mean, these kind of questions, like if you try to relate it to whatever you learn, I think these questions will come very naturally. Oh, I have this nonlinear system, two-dimensional nonlinear system. I could have linearized that nonlinear system, right? And I could have found the eigenvalues. How many eigenvalues that the linearization will have? 2, right? Now this Koopman has how many? 4. Okay, where do I get this 4? I only have, I mean, first of all, are the eigenvalues of linearization will be there in the eigenvalues of Koopman? Right? I mean, are these eigenvalues, where these eigenvalues of Koopman are coming from? I mean, what do they have to do with the eigenvalues of the linearization, which so far people have been telling me that those are like very important, like those are actually is what, I mean, I have designing controllers based on those linearization, and those works pretty well. How those eigenvalues actually relate to the eigenvalues of Koopman? Now I have Koopman in this case, which is a 4-dimensional, and it has 4 eigenvalues. Are those eigenvalues related to, are those 4 eigenvalues related to the eigenvalues of linearization? What do you think? Yes, the eigenvalues actually are there in this Koopman. In fact, it has 4 eigenvalues. So where are the other 2 eigenvalues coming from? So the other 2 eigenvalues are coming from the algebra, right? Oh, it has only 4 eigenvalues, but I mean, the Koopman is an infinite dimensional. Where are the other infinitely many eigenvalues? I just constructed a 4-dimensional, but Koopman is an infinite dimensional. It has infinitely many eigenvalues. So how come only I get a 4 eigenvalues? Not just 2. I mean, first of all, the 2 eigenvalues from linearization are there in this 4 eigenvalues. There are 2 additional eigenvalues. Those are actually related to the 2 eigenvalues of the linearization through the algebra. But this is 4-dimensional. It just happens to be the optimal construction, so to say. I could have actually now use other bases. So I use only what? 1, x, y, x squared. I could use y squared. I could use y cube. I could have keep on doing this, and I could have gotten a larger and larger matrix. And then you'll have more and more eigenvalues. And all those eigenvalues can be related to the eigenvalues of linearization. You see what I'm saying? Yes. I mean, the sanity check is clear. I mean, I think the sanity check, since you're doing in finite dimension, is that this basis that you pick in the finite dimension, they has to be independent, first of all, right? You have picked up what? Yes. No, yeah, that's what I'm saying. This example was constructed in such a way that in this 4 was actually enough. But in general, 4 will not be enough. In general, the infinite, like you'll have to go to the infinity. Okay? All you're doing when you are truncating is that you are projecting that infinite dimensional onto this finite dimensional space. Okay? Onto the finite dimensional space. Does that make sense? They could be linear dependent. They could be linear dependent. Yeah, I cannot say they could be linear dependent. Yes, because the algebra could be linear dependent. In fact, if you are taking a 6, in the 6 it may not be closed, but in the 8 it may be closed. By closed, I mean, what I mean by closed is that the psi which you started with the 1x y x square. If you take this, then you make the Koopman act on these. Whatever you're getting are again can be written in terms of linear combination of these 4. That's what I mean by closed. Now, if you take a 6 may not be closed. Maybe you have to go to the 8 to get it. So, for example, in this case, if I take only 1 x and y, that may not be closed, right? You see, because there is an x square term. So that's why I put the x square in the basis, right? Now, if you took x1, xy, x square, and let's say x times y, that will not be closed. You'll have to sort of find the right pair to make it close. Okay? And in some cases, you will never get close. I mean, most cases, you will never get close. Okay? So you see now how to get the eigenfunction. In this case, the eigenfunctions are exact because the Koopman is closed. The eigenvalues are exact. And hence, the eigenfunctions are exact. Now, the next example I will tell you where the Koopman is never closed. That means whatever basis you pick, the Koopman action of the Koopman on this basis will always lead to some terms which are not there in the basis, right? Because there are only finitely many bases. So the Koopman may not be closed on the finite dimensional basis, right? You know what a close means, right? It's a subspace. It doesn't form a subspace under the action of this Koopman. You'll go outside the space. Okay? So that is the example of this logistic map. xt plus 1 equals alpha xt 1 minus xt. Okay, let's call this as s of xt. And now let's pick this basis in this case. And the criteria I'm using in the selection of basis is that I look at the right-hand side of the system. So right-hand side of the system is what kind of nonlinearities are there? It's a polynomial nonlinearity, right? It's a square. So I'm using a polynomial basis. So let's say I pick a basis like a 3 basis functions, which is like a span of 1x and x squared. Okay, and see what happens. So f of x, the first, so kappa 1 of x equals 1, right? F of x as x, so kappa of f of x is what? Is r or alpha x 1 minus x, right? Which is alpha x minus alpha x square, which is yes. So this is what you have. Now f of x equal to x square. So now kappa of f of x, if you have confusion, maybe I can write on f2, f3. So this is 1, 2, this is 3. So this will be x square, right? So what will this will be? Alpha x square 1 minus x square, right? So this will be alpha x square minus alpha x power 4. No, hold on. Yes, that's not correct. Sorry. So this is basically kappa x square. I mean, think of this x square as a coordinate, not as a coordinate function, right? And that's why this maybe it's better to just stick to the f3. Okay, and then you are evaluating this on this. So this is what f3 of s of x, right? Now f3 is a square, so that means this is s of x square, right? This will be alpha x 1 minus x square. This will be alpha x square and 1 minus x square, which is alpha x square 1 minus 2x plus x square, which is alpha x square minus 2x cube plus alpha x power 4. See what is happening? Sorry? Alpha square, right? Good? Oh, this should be multiplying everywhere, right? Right? Is it correct? Right? I mean, the point is, what do you see now? And now the x cube, x4 is kind of are not there in the basis, right? So this basis is not closed. Now you can imagine, even if I use x cube in the basis, what will happen? You'll get some terms which are not there. So no matter how many polynomial I choose in the basis, this will never be closed, right? It will always be some term. So what you'll end up doing is that you will end up finding a approximation in this case, right? So if you do the math properly, I'm just going to write it down. So the K matrix in this case, if you stick to my notation, which I was using as the column, so it will be look like this: 0 alpha minus alpha, okay? Because this is x alpha x minus alpha x square, and then third will be 0 0 alpha square, right? I'm writing as a column. So 1 goes to 1, that's why 1 0 0. X goes to alpha x minus alpha x square, that means 0 alpha minus alpha, and x square goes to alpha square x square, and these other terms are not there, so 0 0 alpha square. Okay? So this is just a finite dimensional representation of the Koopman in the basis, in this finite basis of 1 x and x square. Okay? Yes. Is it possible canonically what? So in this case, as you can see, polynomial basis, no matter how many degrees or how many terms you use in a polynomial basis, you will always get a matrix which is never closed, right? You can keep on growing this. Yes, then it's that's we already done that, right? In this example. In this example, we already done that. So there is a linear base, so you can just choose a polynomial basis. In this case, a 2-dimensional, so you can do 1-dimensional. So here, these are the bases, and then you always get this eigenfunctions directly. Yeah. Good? Make sense? How do you what mathematically? This is not closed. I mean, that's what I'm saying. You can never find a closed one. Oh, mathematically, you mean, oh, how? So the way you say is that this is the optimal projection of the Koopman operator on a finite dimensional basis constructed using this psi. It's the optimal projection. Yes. Yes. Not closer than any other. Um, First of all, I mean, like the question is hard because you don't know what's the right basis, right? Now you may actually end up using a wrong basis, and then you have to use like thousands of them. But if you're smart, maybe you find a right basis where you just use two basis functions and you're done, right? So the number here is kind of yeah. More importantly, what's the right basis? Yes, it will be problem specific, and then some bases actually like work. So, for example, if you're looking at a system, and if you look at the right hand side, so this is basically where you have the luxury of having the model, right? So, in this logistic example, the polynomial is the nonlinearity. So, I use a polynomial basis. So, those are sort of will capture the right thing. Now, if you have a model where the nonlinearities are trigonometric, maybe you want to use a trigonometric basis, right? But now, if you don't have a model, if you just have a data, then you can use neural networks. So there are papers people have written where you can actually use neural network to learn bases, right? So once you have those bases, those could be now very complicated bases. I mean, who cares? And then you use those bases in the construct of the Koopman. Okay, so finding the right set of bases is actually a tough problem. Maybe I should. You can actually show that this is the optimal, although I haven't proved it. But you can show that this is sort of optimal. We can prove it rigorously also. Yeah, so optimal in the sense that like with this basis, right? Given this basis, these the entries of the matrix I'm getting, these are found in an optimal way. That means these are actually the best coefficients. In this case, I mean, we found it analytically, but let's say if I'm actually doing it from data, okay, then you have basis functions. Now you want to know that what is the best fit, right? Basically, this is in a sense of best fitting. The optimal is in the sense of best fitting. So if you have some function and you want to find and this is basically goes back to the least square problem, right? So forget about a Koopman. So if I give you a function and I say, oh, I don't know the function, but I can sample the data from the function. I can tell you, okay, there's a value of the function at this discrete point. The function is continuous function, but I can know the value of the function. Let's say take a one-dimensional function, and that analogy can extend here. Let's say you have a one-dimensional function, a function of one variable, and you don't know the function, but you know you can actually query it and get a value of the function for any given x. Let's say I know the value of the function at n points, right? And now I want to find the best representation of the function in the finite basis, right? So what you do is that I pick a basis, and then I want to write that function in terms of this basis function. So what I want to do now is I want to find the coefficient in the expansion, right? Alpha I. So f of x, I want to write in terms of summation f alpha I, some psi I, where psi i's are the basis function. Now, what are the best possible alpha i's to fit? And then the problem, you write it as a least square problem. And the alpha i's, based on the sample values of the function at n points, can be found using a least square problem. And least square solution is the optimal projection, basically. And in that sense, this is optimal. Because for this example, we just did everything analytically. But if I could actually query this system, rather than knowing the S of x, I only know the information of the system at x and S of x. I don't know the S. I just know the x and S of x. And I know the S, x, and S of x at n points. Right? And then I asked, okay, what's the best Koopman matrix I could get? The best Koopman matrix with this basis functions of 1, x and x square will be the optimal projection. And that again is the least square problem. We'll talk about the least square problem when we talk about the finite dimensional approximation, maybe tomorrow. Okay? Yes? So I will talk about that. So it's a good question. I have some ways of actually sort of computing them. So rather than saying that I can tell you the analytical form of the basis function, I can tell you the value of the functions. You see what I'm saying? So one thing to say is that, oh, I say is a sine of x function, right? So that's like a analytical function. When I say, oh, I'll tell you the value of the function, give me any x, I'll tell you the value of the function. So that is doable, I feel. Okay. To find the analytical, I mean, once you know the value of the function at a sufficient point, maybe you can try to find a best fit. That's another problem. But finding the analytical form of function is tough. Okay. Yes. That will be a closer representation of the true infinite dimensional object, right? Because I mean, for this example, I can speak. In general, I mean, I would say here, I mean, more the merrier, right? Because you see, I mean, as you increase the size, you're getting closer to the true, right, reality for this basis. So, I mean, it all boils down to how much computation you can handle, right? How much computation you can handle. And in this case, this is an analytical example where you can actually see the structure. You can see the structure here. If you just carry one more step, you see, oh, this matrix actually grows like 1, 0, 0, 0, alpha, 0, 0 minus alpha, alpha square, and so on. So here you will see the structure. And maybe that structure itself is good enough. Okay. But in general, I mean, if you ask the question in general, given a fixed basis, more terms, or given a particular structure of the basis, let's say polynomial basis, more terms I add, larger and larger matrix I would get, and that matrix will actually, and there are theorems which actually tell you that, okay, this is actually sort of approaching the true Koopman with such and such rate, and so on, right? So the one results which are very well understood, which will kind of get there as it comes to data, right? So which is actually very well understood. The basis actually is little still actually unclear. So because this is all sort of motivated by data driven, like I'm assuming that I don't have a model, and you give me n data points. Now there are two approximations that are happening, right? So one approximation is happening because you're using finite basis. The other approximation which will happen is because you have finite data. You don't have the true model, but you only have a data from the model. Now, how the approximation error actually behaves as a function of data and as a function of the number of bases. So as a function of data, these actually problems are very well understood. As a function of basis, also they are well understood, but they are again sort of restricted to that particular basis, right? If you change the basis, everything sort of you have to start from again. But as a data, actually, these are well-structured problem, well-studied problem, and nice results because of the fact that this problem is actually eventually reduced to a least square problem. And I think all the convergence rates that you have for the least square problem actually carries over to in this setting as well. And that's the beauty of this linear framework, is that many of the things which are actually like, for example, least square actually applies here, like convergence rate. What are the rate of convergence of this Koopman to the true Koopman in terms of the data length? Those goes like 1 over square root of n, right? So those are nice results. Okay? And so I don't know how many of you are familiar with, I'm sort of doing a little tangent here. I don't know how many of you are familiar with the kernel methods. Are you guys heard about kernel methods? In kernel methods, actually, you don't use finite basis, you use infinite basis. So all these problems are actually arising because you're using finite basis, but you don't have to do computation in finite basis. You can actually do computation in infinite basis, which is basically what kernel does. If you know about support vector machine or kernels, that's the beauty of this kernel methods, right? I think the kernel methods can also be used in the approximation of Koopman operator, just like you use kernel methods in the approximation of the, like in the classification problem, right? The kernel methods are also used in the Koopman operator, Koopman approximation. And the advantage of kernel is that there are infinite bases. You are working with feature maps. There are infinite bases. So those problems actually using finite bases are actually becomes mute now, because you are working with infinite bases. Only problem now is becomes a data, finite data. You see? But again, I mean, what's the right choice of kernel? Nobody knows. Those problems are there even in the classification problem. Nobody knows what's the right choice of kernels are. Same thing applies here as well. Okay, so the finite basis is just sort of like a baby step towards computing this, but now people are doing all sorts of crazy things when it comes to approximation. Kernel tensors on drugs, basically. These are all sort of computational methods on, yeah. So anyway, so this is what we have. I wanted to actually now jump to a continuous time system. How are we doing it? So we have 15 more minutes, right? So I want to talk about the continuous time system. How does this thing actually works in the continuous time system? Continuous time system has more structure, so this Koopman will also have more structure, right? And when you do this Koopman in the continuous time system, you will see things which you have seen. You will see things which you are familiar with. Some of the things, at least some of you, and then you will kind of see this Koopman in a new perspective, okay? Because you could actually relate to something that you already seen. For example, I don't know how many of you are familiar with PDEs, partial differential equations, or more specifically, advection diffusion, or even advection type of PDEs. So I think those kind of things you will start seeing now, and its connection to the Koopman when it comes to continuous time. Okay. So just like what Arun talks about, actually, he spent quite a bit of time yesterday when he talked about this flow, right, of a dynamical system. And then, so you have a dynamical, you have x ortical f of x, you have flow of a dynamical system, so the flow is actually, so those who have done PDEs, they will actually get this language, right? So there is a language the PDE community use, and that language actually is what we're going to use also. It's just a language, right? It doesn't have to be, if you don't know it, that's fine, but if you know it, it actually makes life easier, right? He talked about this idea of the flow, which actually has a group property, right? So there's something called as a group when he talks about the flow. Differential equation, flow, group. In a PDE, they talk about generator of a semigroup. So you have a PDE, then there's a generator of a semigroup, and then there's a semigroup. So how does that relate to Koopman? So Koopman, for a continuous time system, instead of talking, let me just write it down. So let's say we have a continuous time system. X dot equals f of x, right? Now, the flow is denoted by phi t of x, right? What is a flow? Flow is a solution, right? Which we have done. Now, this, in the discrete time case, you have one Koopman operator, right? Because the map is just one time step map. In a continuous time case, because it's not a, so this phi t, what is phi t of x? If you think about it, what is phi t of x? Like I told you, right? So what it does is basically you are at x, and phi t of x tells you where you will be after time t, right? Now t, what is t? T is a time. Where what value the t can take? it can take both in the continuous in the ODE. The t can take any. T belongs to R. That's why it's called group. It can take both positive and negative time. You can go both forward as well as backward, right? T belongs to R, okay? Otherwise, if T is only positive, then you call it as a semi-group. And that's what the PD use, because PD, they don't use the backward time. They don't go negative time, okay? That's why it's called a semi-group. Anyway, so this T belongs to R. So the point is that in the continuous time dynamical system, you have a flow. So the phi t of x, if you think about it, if you take t to be only integer time, what do you get? If you take t equal to 1, it becomes a discrete time system, because you are at x, phi t equal to 1, phi 1, x gives you a next point, right? T equal to 1 is just a arbitrary, you can take t to be delta t, whatever you want, right? So you get a next time, so it becomes a discrete time. But now t is taking a, so if you have discrete time, then you get only one Koopman operator. But now t is taking a continuous time. So what you will get? You will get a family of Koopman operator. Okay, you get a family. As you change the t, you get different Koopman operator. Same, but it just, so the notation is that Koopman operator becomes a group. In this case, actually, if you look PDEs, if you're strict, then you call a semi-group, but because this flow is defined for both positive and negative time, I will just use the word family of Koopman operator. Okay, so KT of f of x, what do you think this will be? Just based on a discrete time definition, will be f phi t of x. Right? Because if you take t to be 1, is reduced to a discrete time. Okay, and t here, superscript here, signifies that I can take any time t. Okay, I'll call it family of Koopman. Oops. Okay, and continuous time. Function of time, I mean, it's a family of Koopman operator. That's the language they use. Instead of one Koopman operator, you have a family. As you change the t, you get things, right? Yeah. Okay. So now you may have known this, but may never have paid attention. What is the connection between phi t and this x dot equal f of x? Like when you say phi t is a solution, what does it mean? Yes, right? So the x dot equal f of x, x here is just a variable, right? So what it means that d phi t of dt equals f of phi t of x, right? Right? Now what is this f here? F is what is, if it, they don't use language like this, but that language is what is I'm going to use in the PDE and in the Koopman for continuous time. F is actually a generator of this flow. F is what is generating this flow, right? Because there is a vector field and a vector field is generating this flow, right? So the another way to write this will be so what is f of x? F of x is, if I want to write in terms of limits, f of x will limit t goes to 0, phi t of x minus x divided by x. Sorry, divided by t, right? Right? So this f of x is what is called a generator of the flow. So this right hand side is basically nothing but d phi t by dt, right? This is the calculus. Okay. Now replace this phi t with kt. So kt is also a flow. If you think about it, it's a flow in the space of functions. So I could do limit t goes to 0, kt of some minus identity acting on some function, let's say psi, divided by t of x. Right? This is basically, I'm writing as limit t goes to 0, kappa t psi of x minus psi of x divided by t, right? So just like f of x is a generator for phi t, what we are trying to do is here is trying to find what is the generator of kt. Make sense? What is the generator of kt? What is the generator of kappa t? Okay. It turns out the generator of kappa t is, what is this? This is nothing but limit t goes to 0, psi phi t of x minus phi of x divided by t. Okay. This is equal to f, and now this is basically what notation you prefer. Some people use one notation, some use other. You could write it, I'll write both of them. This is nothing but partial psi partial x f of x. So partial psi partial x is a convention, will be like a row vector, f of x is the column vector. So this is a dot product. Okay. Or you can also write it as f of x dot gradient of psi. So the generator for the Koopman, so the family of Koopman operator is this. This is the generator, okay, which is f dot del, f of x dot del. What does this have? Have you guys seen this before? This is the advection operator. It's like sort of, if you have a incompressible flow, right? This is a divergence free flow, and if you are putting something, I was giving the example, like if you put an ink in a flow, and if the flow is volume preserving, which is the divergence 0, then the way the fluid, like the way the ink will propagate, will be using this operator. Okay, so if you want to think about this, this is actually let me just give the terminology, then I'll spend a little more time. This is called as the Koopman generator. So this is the Koopman generator. So kappa of t is your Koopman operator, and Koopman generator is given by f dot del psi. So the Koopman PDE, so you can also do a Koopman PDE, which is basically partial psi partial t xt equals f dot del, let me use some other phi here, so not to confuse. I'll tell you what this is, phi partial phi x f dot. So what does this tells you? That let's say if I have some initial condition x0 as some phi 0 of x, so I have some initial function, and I want to know how this function will evolve at certain time t according to this PDE, right? Phi at x of t is the evolution of this function phi 0 of at time t equal to 0. So this is given by the solution of this PDE and is of the form phi 0 phi t of x. That's the Koopman. I think I'm going very slow. I couldn't cover what I wanted to cover. But I think, I hope whatever I've covered actually is, you got it, because I think it was very important to get it. I haven't gotten to like the other operator which I was talking about, the Perron-Frobenius one, which actually is a dual to this. And that is actually, if you think about it, this operator is actually, Koopman is, while it is easier to describe, by that I mean it is easier to write, but it's actually a more abstract one. Okay, the other one is brother or sister. The Perron-Frobenius one is actually more complicated to describe, write down, but it's actually much more natural. And these two are actually dual to each other. Okay, and it's very fascinating stuff with these two, the way they actually play a role. In fact, whatever we have done so far in controls, like it all has to do with the Koopman operator. Like by that, what I mean, let me say more precisely, the Lyapunov function is all Koopman. The Hamilton-Jacobi equation is all Koopman. But all these things, the Lyapunov has a dual, the Hamilton-Jacobi has a dual, they can be written in terms of the Perron-Frobenius. Okay, almost maybe I don't know. Should we do more? Maybe tomorrow afternoon sometime. I have to do for the. Okay, at least an hour to talk about, because tomorrow I'll start with the Perron-Frobenius because I want to talk about that. So whatever remains, then maybe I could do in the afternoon. Okay. So anyway, I think this is what it is. Any questions so far? Yeah, I want to do some examples. Maybe I'll do it at the beginning of the next class tomorrow, and then I will do the Perron-Frobenius. So what I want to talk about tomorrow is how to do the finite dimensional approximation. And I think there are all these minor details. If you are interested, we can actually go into the depth of it. And I think that's maybe where I can save a lot of time. Is that the big picture is that finite dimensional approximation of these operators is basically solving a least square problem. Okay? Because these are linear operators. Because these are linear, we can always write the approximation problem as a least square problem. I think that's the big picture. And then there are all the other details, okay, which some of that we can actually skip and save some time. Okay. So yeah, I mean, if there are no questions, then we can stop here. Yeah. Exactly. So you'll see, that's what I was saying. You will kind of see. So the right hand side is precisely Lie derivatives of the function phi in the vector field of f. Yes. So you can also write this as in the Lie derivatives definition or notation as this. Yes. And that's why I'm saying I think the Lie derivatives is sort of there in Lyapunov functions, and it's just a writing, right? So that's why I'm saying whatever we are doing, a lot of things we are doing in controls, the Hamilton-Jacobi equation, these are two equations I think everything is sort of based on. Lyapunov equation, Hamilton-Jacobi equation is all based on the Koopman, like one way or the other. I mean, it just provides you a different way of looking at things, and then it kind of then allows you to look at this from a data point of view. But I think that's one point, but the other thing I want to mention is that, but this is not a very natural way to look at it. Although we are using it so often, it's not a very natural way to actually look at the linear, the operator. The other way is actually much more natural, but that is never used. The Perron-Frobenius is much more natural, but that is never used. And there are some advantages. So I have some papers on using the other approach. The other approach actually has some advantages in terms of like the classical problem in the controls when it comes to control design. Like let's take a plain vanilla problem of control design in the in nonlinear control design in using Lyapunov function. So the nonlinear control design using Lyapunov function is actually a non-convex problem because you cannot find a Lyapunov function and controller simultaneously. You assume either a control Lyapunov function and then you find a controller, but then if that doesn't work, then you change the control Lyapunov. So the classic problem of designing a controller and a Lyapunov function, finding a Lyapunov function, is actually a non-convex problem. But if you now write this problem in a dual setting using the Perron-Frobenius, it becomes a convex problem. So actually you get a lot more benefits if you actually look at this problem from a dual perspective using the Perron-Frobenius. And I think it's not just like, so the duality actually gives you something meaningful for the synthesis as well. I'll touch upon that, maybe not to go into detail, but I can always pick up that discussion offline if you guys are interested. Okay, thank you.